decomposition. And so 1 tau bar would become Z after the condensation has occurred. Tau bar would decompose into 1 plus X. Tau 1 is equals to Y, and tau bar is again 1 plus X. So assuming that fusion stays associative, so we would end up with Z plus Z times X equals to 1 plus Y plus X. So now, this gives us some consistency conditions on what this Z and X has to be. For example, Z is non-trivial. It has quantum dimension greater than 1. So Z cannot possibly be this 1 here. So it means that Z plus X must be able to fuse into 1 plus either Y or X. So let us make the assumption that Z plus X, Z times X is equals to 1 plus X. Then this other Z here would have to be identified with the piece of Y here. Now you could repeat this exercise and then look at the fusion relations of tau bar times tau bar. And then you would get 1, 1 plus tau 1 plus 1 tau bar plus tau bar. And then again, I replace everything by the decomposition here. And then again, using the assumptions that the results that I've got here and plug it into the new set of fusion relations from the original theory, then it's not hard to convince yourself that at the end of the day, there's one unique solution to this set of fusion rules between X, Y, and Z. So what you're going to get is the following. So here we have already identified Z with Y. At the end of the day, all you're going to get is X equals Y equals Z, and also XX equals 1 plus X. So note that we started off with 2 copies of the Fibonacci theory. After we have chosen a condensate tau bar, you end up with a fusion algebra of 1 copy of the Fibonacci theory. X behaves exactly like the Fibonacci theory. Okay, so now the next question is, what do I say about non-members being having non-trivial statistics with members? This X here belongs to this X here came from both 1 tau bar, tau 1, and tau bar. So what is this X confined or not confined? This is the crucial question. And Bayes also give a very simple rule to determine whether this X is confined or not confined. The point was, X has 3 parents: tau bar, 1 tau, and 1 tau bar and tau 1. And these 3 things all have completely different statistics. So what that means is, naively, you would have expected that after I have a condensate, the statistics of the particles are just inherited from before the condensation has occurred. But now X does not have a well-defined statistics. It has 3 different parents with 3 different statistics. So the rule that he came up with is that if a particle does no longer have a well-defined statistics because the parents have different statistics, it must be a confined particle. So now, so what have we got after we have completed this exercise of condensing tau bar? We end up with only 2 different sectors, 1 and X, but then X, we argue that it has to be confined. Therefore, we have satisfied basically all the conditions here. We end up with, in the condensed phase, there's only the trivial sector 1 that is unconfined, but then everything else left behind, which is X, has to be a confined particle. So,
can you explain? So, how do you understand why X has to confine? When you condense tau bar, I mean, it's an intuitive picture why X has to confine.
The intuitive picture is that okay, let me try this intuitive picture first. The first intuitive picture was you have to identify X, Y, and Z up to fusion because of fusion with tau bar. And these three things have completely different statistics. So when I want to define self-statistics of this particle, it is no longer defined up to fusion with tau bar. So it must mean that when I want to cross the condensate, if it has no self-statistics, then it probably means that it has non-trivial braiding with the condensate. And
tau bar.
Yes. But then the only twist in the story is that tau bar also participate in this X. Right. So now we have identified our Lagrangian subset in this model. It is 1 and tau bar, and we have argued that there is no non-trivial sector that remains that is local that could pass through the condensate. So now we could come to the second part of the story. We have to count ground state degeneracy. Yes. It has a quantum dimension equals to, in fact, greater than 2. It is equals to gamma, the golden ratio plus 1. So only if it has quantum dimension greater than 2 can it split into two different things, each with quantum dimension greater than or equal to 1. So now it comes to this second part. We have to do ground state degeneracy. Let us also still put the stuff on a cylinder. Here, we don't have many choice for boundary conditions. We only have one, we came up only with one set of the Lagrangian subset. Let us call this L tau. So we're forced to put the same boundary conditions on both boundaries. So now we can repeat the exercise. When we count ground state degeneracy, we build a ground state basis by winding non-trivial Wilson lines around here. But now, what are these non-trivial Wilson lines? They are precisely the confined sectors that I'm left with after I have put in this condensate. And recall that after the condensation has occurred, I only have two different sectors, 1 and X. So this tells me that the ground state degeneracy is equals to 2. Now we can compare this answer with the charge transport picture. So L tau, the Lagrangian subset, has two Anyon, 1 and tau bar. So if I count the number of charge transport that could occur across this boundary, you would again conclude that 1 and 1 contribute to one channel, and tau bar fuse to also contribute to one channel of 1. And so from the charge transport picture, you again come to the conclusion that the ground state degeneracy is equal to 2. So that is very nice. But then the question is, are we sure we have got the right answer? And how do we check that we're not doing something stupid? Fortunately, in this case, we can actually check the answer and know that we are doing the right thing. The reason is we're looking at the model Fibonacci times Fibonacci bar, the time reversal. So we could think of this cylinder as coming from two cylinders. And this second cylinder is the time reversal of this cylinder. And we're gluing these cylinders with some boundary condition such that everything, when we have glued them, everything is gapped. So at the end of the day, you could think of this guy basically as one copy of the Fibonacci model placed on a closed surface on a torus, where there is no gap modes anywhere. So basically, it's just one single copy of the Fibonacci model on a torus. Everything is gapped out. And what is the ground state degeneracy for one copy of the Fibonacci model on a torus? It's exactly 2, because we could build 2 ground states using these Wilson lines, 1 for tau. So we come up with precisely the same answer, and we know we're on the right track. In fact, you could do that for an arbitrary number of holes. And every time you see this picture, you just turn it into two copies of the picture and glue it into a closed surface with higher genus. And it is not hard to convince yourself that precisely because this condensed phase has exactly the same fusion algebra as one copy of the Fibonacci model, you would actually end up with exactly the same counting as if you have one copy of the Fibonacci model in this closed higher genus surface. And so this tells us that we're on the right track, or we have we at least produce the right answer that can be cross-checked by well-known results. But this is not the end of the story. So now it comes to this twist of the story that we had to make use of this Laughlin-Boutao experiment, a thought experiment, to get to the final answer, to put in this final piece of the puzzle. So let me add that, in fact, there is a theorem, I think, that says that if I have a model multiple times the time reversal, and I condense only the diagonal anyons. Diagonal anyons are the analogs of tau bar. If you can so all of these things would automatically have bosonic trivial self-statistics. So there's a theorem saying that if I condense only the diagonal things in a model times the time reversal, the final fusion algebra is always equal to just one copy of the model. Exactly as in this case, once I condense tau bar, the fusion algebra is equivalent to one copy of the Fibonacci model. So you could see that the way the arguments of this Anyon condensation, at least for this product models, would automatically reproduce all the well-known answer for a single copy of these models on closed surface. So that is a cross-check of an infinite set of models saying that this produced the right answer. But now let me go to this more interesting answer. How much time do I have? 7. Oh, good. So now I'll come to this more interesting example, and this example taught us this idea of multiplicity. So this interesting example that we are going to look at is the so-called the twisted gauge theory. Twisted gauge theory of C2 cross C2 cross C2. So all you need to know again is the anyons in this problem and also the statistics of the anyons. And now for non-abelian models, we also need to know the quantum dimension, and that gives us knowledge about how things split. So in this model, there are electric charges. And these electric charges can be parameterized by 3 numbers. So A, B, C can either take values 0 or 1, corresponding to the charge of each of these C2. So there are 8 of them. And the trivial sector corresponds to A equals 0, B equals 0, C equals 0. And these guys, the electric charges, have statistics equals to 1. All of them behaves like bosons. What is special about this twisted quantum double model is that it has a set of dions. These dions comes in 2 sets, plus minus, and M and M also is labeled. M is kind of the magnetic charge, and it is also labeled by 3 numbers. But A and B and C cannot all be 0, so there are only 7 of them. And the quantum dimension of the electric charge is 1. They behave like bosons, and they are abelian. But the dions, they have quantum dimension equals to 2. So this gives us the potential that these things might split into 2 different things. And Okay, so then I should also talk about the statistics of these ions. If so, the statistics. If A and B and C are not all equal to 1, then the plus dion behaves like a boson, and the minus dions behave like a fermion. But then when A and B and C all equal to 1, then it would behave like a sambion. So these are the basic topological data of this model. So one very trivial way of condensing things clearly is to allow all the electric charges to condense, in which case all the magnetic charges would condense, and going through this exercise as we did in the Fibonacci model, it's not hard to convince yourself that these dions, so I would condense the set that I would have corresponds to all the electric charges. If you do that, then all the dions would split. They would split into two things. Let me see. Right. These dions would split into two things, but these two things are actually identified. So if I put these things on a cylinder, then I would find that I would have exactly. If I put the electric condensate on both ends of the cylinder, I would end up with, okay, so M1, M2, M3. I would end up with the conclusion that there are 8 fusion channels that could take me to 1, so GSD is equals to 1. But if I also count the number of confined anyons, all of these things are confined. Oh, sorry. Thank you. If I also count the number of confined dions, you would also altogether including the trivial sector, I would also end up with the answer 8. So here, so far so good. But then what is interesting is that you can see that theta m is equals to plus or minus 1 depending on this label. So there must be some more non-trivial choice of condensate. So the next thing we tried is to look at a dionic condensate. If we choose, let's say, D plus 100 to condense, this guy has quantum dimension 2. So from the rules that we discussed, this guy has to split into 2 things. So one of the things that it has to split to is clearly 1, because I'm making it to condense. So it would split to 1 plus some other thing that, let me call it C. All other anyons would also potentially split into 2 things. So let me. So what we did is that so there are lots and lots of anyons, and these things have pretty non-trivial fusion algebra. But if you work things out very carefully, you would end up with the following conclusion: C has to be, for consistency reasons, C has to be equal to 1. C has to condense. So what happens is that D plus split into 2 things, but both of them are condensates. So in a way, this has multiplicity 2. And then E100 would be equals to something that we call D. And this D is identified with the D's here. And so for E equals 0 AB, all of this would have to condense at the same time. So, so now let us do a ground state degeneracy counting. The first way we count is to count the number of confined sectors. And so we find that this D100 gives a D, and so we have D, and then this D1 AB, so there are 3 of them. So D is one sector, D1 AB is another sector, D2 AB. So there are 3, because AB cannot both take value 0. So A and B could be either, both A and B could take value 0 or 1, but they cannot be both 0. So what we have is that this D plus or minus 0 AB split into 2 things, and this D1 is not identified with this D2. And so here it gives 3 sectors. This guy gives another 3 sectors. This is 1 here, and then the trivial sector. So altogether, we are left with 8 sectors, 6 plus 2. So now let us, on the other hand, look at fusion channel between the boundaries. If we look at the fusion channel, the set of condensates includes D plus 100, and then E0 AB. And of course, the trivial sector 1 is also there. And let's choose the same boundary conditions on both sides. So if we count fusion channels, this 1 contributes 1, E0 AB contributes 3, and D10 also contributes 1. So if I count fusion channels, I would end up with a GSD counting equals to 5, and it does not match with this 8 here that I count by counting the number of confined sectors. And so that was what prompted us to think that something is wrong. It doesn't make any sense that the 2 counting is not matching. And so, the new twist in this story is that we noticed that D plus split into the condensate twice. So what if we count D plus as 2 objects? If we count D plus as 2 different objects, then the fusion channel from D plus alone would give rise to, instead of providing only 1 fusion channel, it would provide 4 different fusion channels. And if it provides 4 fusion channels, combining with the other fusion channels that we already have, we would exactly have 4 plus 4 equals 8. So this tells us that the multiplicity of how many times a condensate participates as a condensate is an important piece of information that directly changes the ground state degeneracy counting. And then if we put in this extra piece of information, we would recover this correspondence between charge transport and flux for these non-abelian theories. And we have checked this claim using some other more non-trivial model, and each time it works, so we believe it's correct. And more encouragingly, Professor Wen also came up with a completely independent method of computing this ground state degeneracy, and it appears that we have a precise matching even for this model. So, so we believe we have got the story right. So thank you very much. Yes, yes.
Number one, tau and tau one.
Right.
So, whether tau also condense?
It does not condense. So the important point, the important rule that Byers came up with is that because tau bar cannot completely condense, so he claims that tau bar under condensation splits into two things. Part of it condenses and part of it confines.
Oh, I see. So, I see, but which part condense, which part?
Right, so the way we work that out is to say, let's assume that it becomes 1 plus x, and I don't know what x is. And then, using the original fusion rule, like tau bar becomes everything, then we replace each tau bar as 1 plus x, 1 plus x. Then we could work out the fusion rule of x and x, how it relates to the 1 tau and tau 1. And so that was how we conclude that we end up with
So the tau bar became 1 plus x and a 1 condense.
and x confined. Yes.
Any other questions?
Yes. In the first part of the story about the Anyon condensation, does it cause the gauge field to become massive?
Does it cause the gauge field is already massive? It's a Chern-Simons theory.
Chern-Simons theory is a massive gauge field.
Yes. It's already a topological theory. There's no dynamical degrees of freedom.
And this, is it a spontaneous entropy? It seems you've got the gauge field, you write, let's say a pure gauge field, right? Then finally you got some non-zero values.
Right. Because in the presence of the boundary, it is no longer gauge invariant, so it becomes anomalous. And this is a description of the anomalous modes in that cancels the anomaly, the boundary.
So there's no connection to these mechanisms.
It has, you mean the presence of these modes?
I'm
Or
just thinking.
the gapping out, I'm trying to argue that it is direct, no, it's not X mechanism, sorry. No, it's not.
Any other questions? Okay, if not, let's thank our speaker again.